place. All right, here we go. So first question, let's make this a little bit bigger if we can. Not that, I want it just a little bigger. Why is it not making bigger? All right, got to do this. It's on that. I just want it to be a touch bigger. Not. Cancel. All right, you got it on your paper. It's okay. All right, list your 6 strong acids. So, Austin, I want them from you today. What are they? I want them from you today. What are they? HNO3, HCl, HBr, HI, H2SO4. Thank you. Okay, so let's talk about these. These guys come from the periodic table, do they not? And what is the name, Skylar, of HCl? Okay, how'd you know that? Because you wrote it down, okay? Kyle, did you know HCl is called hydrochloric acid? Okay. Did you just know that because that's probably the most common acid you know about it? All right, so, Hayden, what's the name of HCl? Okay, how do you know that? You mean you didn't just extrapolate from HCl to HBr and you say, well, since hydrochloric, it must be hydrobromic? Mariah, what's the name of HNO3? How do you know that? But that surely doesn't sound like hydronitric acid. That's just nitric acid. So that's a little different. How do you know that? Okay, good deal. All right. Kelsey, what's the name of HClO4? How do you know that? Oh, okay. So there is a naming method for naming acids because these 3 are called hydrochloric, hydrobromic, hydroiodic. Okay? And this fellow right here is also an acid. You might not know him because you might not know that Cn to the -1 is known as cyanide, but HCN is called hydrocyanic acid because it's made with cyanide. HCl is called hydrochloric acid because it's made with chloride. HBr is called hydrobromic acid because it's made with bromide. HI is called hydroiodic acid because it's made with iodide. Did you hear anything in that? Ide. There's the key. If the anion with your hydrogen has the name that ends in IDE, then you put the prefix hydro on the front. The only time. Hydro on the front. And then instead of IDE, we take off that IDE and just put on IC. Hydrochloric acid, hydrobromic acid, hydroiodic acid, hydrocyanic acid. So if the anion ends in IDE, you do use that prefix hydro. This doesn't have hydro on it. This doesn't have hydro on it. This doesn't have hydro on it. Kyle, why? Okay, so they don't have an ending in their anion of IDE, but Cn -1 is not called periodic table here. Polyatomic ion that didn't make you memorize, because we don't see it very often. We usually see it here, and this is the only place you see it. We don't even memorize it. Okay, so if it ends in IDE, the anion, then you add that prefix hydro. Okay, so Mariah, you said this guy was called what? Nitric acid. All right, so Mariah, who is in him anion-wise? Who is the anion with the H? Nitrate. And he's named what? nitric acid. Hayden, who is that? ClO3. Who is ClO3 minus 1? What's his name? No. What is the name of ClO3 to the minus 1 charge? Who is he? Chlorate. Guess what the name of this guy is? Chloric acid. He can't be hydrochloric because that's hydrochloric. This is just called chloric acid. Nitric acid. Sulfic acid. I know that doesn't sound right. They didn't like that way back when either, so they added in a little UR. But technically his name is sulfic acid. They decided to change it to sulfuric because they liked how that sounded better. Okay? Now, who is ClO4 minus 1, Stephanie? Who is ClO4 minus 1 on your polyatomic ion list? Who is ClO4 minus 1? Who's he called? Perchlorate. And this acid is called perchloric acid. So you see how that rule works? If it ends in 8, the anion part of your acid, all you do is take off the 8 and just put on a little ick, and you're done. So perchloric acid, sulfic acid, nitric acid. And I know he's sulfuric, but I'm using that to drive home the point. There's a rule, there's a plan in place for how to name acids, and you have to know that. For the OWL, you definitely have to know that. For the AP exam, you have to know how to name your acids. All of them. All of them. That's why you got to know your polyatomic ions. All right, good. Now, the next thing I asked you to do, that takes care of some naming issues. The next thing I asked you to do was to show me the dissociation equation. So, Michael, which one did you do, and what did you write down for the dissociating of one of your strong acids? Okay, HCl. So you wrote HCl here. What did you write down next? You put aqueous. Okay. I didn't hear. Yields. Good. One arrow. One arrow. Why one arrow? Because he's strong. Okay. Then what did you write? H plus. Okay. Did anybody do anything different? Because that's one way. There is another way. Did anybody do the other way? Or did you just do that way? What other way did you do it? You did it another way. What way did you do it?
I did HCl plus H2O.
Ah, okay. So he did the other way. This is called the Arrhenius way. And this is absolutely 100% correct. Matthew is doing the Bronsted-Lowry way, which is absolutely 100% correct. And you wrote down HCl plus water. Okay, and this is aqueous, and this is a liquid, yes. Okay, and you drew an arrow, and then what did you write?
H plus, or no, H3O plus, sorry.
Okay.
Yeah, I didn't do very much. That's why it's plus Cl.
What is the difference, Jordan? It's not just O. Look again, Jordan, look again. Compare the two. What is different about the two? Hydronium and water. Hydronium and water is the difference. So Bronsted-Lowry says when you do the dissociation equation, you write in water after the acid. And so that over here, instead of just writing H plus, you show the H plus attaching to the water, making what we call hydronium. So let me just show you a quick visual of that. There's water, yes? In his nice bent form, yes? And here is an H plus that comes along and just says, I'm going to share that lone pair of electrons that you have oxygen. I'm going to share that pair. So it actually turns it into this, which is no longer bent. Turns it into that, which we put brackets around it to represent that now it's got a +1 charge. And what shape is that? Triangular pyramidal in shape with only one lone pair of electrons, yes? Okay, so I wanted you to see what's really happening. The hydrogen's just coming along for the ride. Water's letting him. The hydrogen's just sticking to the H2O like a cowboy on a horse. Doesn't that sort of look like a horse? Look at it. Kind of big, long, bent legs. And here's your cowboy just going along, riding on the horse. Now, I really don't care how much water there is. There can't be any more H3O plus than there is of H plus. So, whether you see it as H3O plus or H plus, it means the same thing. It means hydrogen ion or hydronium ion, but they mean the same thing. They are the same thing. I know that sounds funny. We don't care about the horse. We care about the water. We care about the H pluses, the cowboys. Can't have any more cowboys on horses than you have cowboys. Plenty of horses around in that solution beaker. But it's just the H pluses that matter. So whether we write them as H plus or H3O plus, it means the same thing. Can you handle that? Yes. Can you handle that? Whether it's Arrhenius or Bronsted-Lowry, the dissociation equations mean the same thing. Can you handle that? Okay, yes. Nope. You're going to see Bronsted-Lowry a lot. But you might see from one of those old geezers that puts together those AP exams that you take, you might see the Arrhenius way. But the new fad is Bronsted-Lowry. You should know both. You should know both. And whichever one you choose to use is up to you, but you should know both, particularly Bronsted-Lowry. Okay, yes. No. No. You mean here?
Yeah.
No. Once you have a plus here, there is no more. No more. Okay. Let's do one more. Jordan, give me one more to do. One more strong acid to do. Perchloric acid. All right. Do you want to do Arrhenius or Bronsted-Lowry? Arrhenius. ClO4 yields H plus ClO4 minus. HClO4 yields H plus and ClO4 minus. All right. So I need some help, Skylar. How's that going to look in Bronsted-Lowry form? Because this is Arrhenius form. How's the Bronsted-Lowry form going to work? Or look? Excuse me. Okay. Thank you. Y'all can handle that, yes? That's dissociation equations, which we've already done in the past. It was just a long time ago. Those are my strong acids, Jordan. Yes, you may go. Okay? So everybody with me so far? Okay, so the next question says, list 4 weak acids. So, Abby, I need a weak acid. What weak acid did you come up with? H2. All right, so H2PO4? H3PO4, good. All right, phosphoric acid. We like to call them phosphoric, it sounds better, but phosphoric acid. All right, Mariah, what's another weak acid that you came up with? HF. Hydrofluoric acid. Kelsey, what's another weak acid you came up with? Okay, chromic acid, good. H2CrO4, good. Ira, what's another weak acid you came up with? Yes, H2CO3, good. Okay, so let's do the dissociation of a weak acid. There's a ton of weak acids out there. Tons and tons and tons of weak acids out there. The only ones really technically that you might see from the table beyond HF would probably be H2S or H2SE.
We ever see the hydrated aluminum 3 ion?
No, we talked about that Friday night at the dining room table. No, we're not going to see that. No, in the past we did, and they've taken that away. All right, so let's talk about HF. HF, Arrhenius way. I need some help, Brianna. Show me him dissociating the Arrhenius way. Okay, that's the Bronsted-Lowry way, and that's okay. What kind of yields? A double yields. He's not strong, thank you. Good. All right, Hayden, I need the Arrhenius way for HF. Okay, so see, literally, you've got those two things showing up on the product side with F minus. So in my Ka expressions that I would end up writing, it doesn't matter whether I choose to write H3O plus or H plus, they mean the same thing. Because you can write it either way, and either way is valid for the dissociation. Okay, so Narique, you missed that. You might have to go and look at my little tape that's going on. Okay. Okay, good question. We're getting ready to look at one of those. All right, so now, let me take my eraser. Well, citric acid, but then there's other kinds of acids. There's actually, there's ketones to give us the smell of our fruits. Ketones, and that's organic.
They actually need mice to be repulsed by fruit by hearing ketone shock.
Oh, good deal. All right, let's look at one of these. It's pretty common, carbonic acid, okay? Carbonic acid. How in the world do I show that dissociation? And I'm going to make a loud statement here. Are you ready? 1 hydrogen at a time. How many hydrogens at a time? 1. That means you've got 2 dissociation equations you can write. But you do it 1 at a time. All right, Matt, help me out. What do I write on the other side? I'm doing Arrhenius way just because I want to. Yeah, in fact, you know what? I need to do the other one, so that's good. Well, all right, we'll just come down here. H2CO3 plus water. Okay, and I write the double arrow. And what do I write next? 1 hydrogen at a time. 1 hydrogen at a time. See, there's 2 hydrogens to give away, and only 1 can come off at a time. But this is an acid. It's not a base. We're trying to make him a base. He's an acid. So he donates an H+. H2CO3 is going to donate 1 hydrogen at a time. Okay, good. So that leaves me HCO3 with a -1 charge. And where did the H go? Okay, so now he's riding on top of the water like a cowboy on a horse, and we call him hydronium ion. We don't know hydronium ion very well because we don't do that in regular chemistry. All right, there's the first dissociation. There's a second dissociation. So Matthew, tell me what to write for the second dissociation. What do I do?
Well, you've already got
Got the first one right here.
Where are we doing?
No, we're not doing Arrhenius. We're doing Bronsted-Lowry for H2CO3. That's the first dissociation. But there's still more hydrogen to come off. So what do I do now? I add water again. So I bring that fellow down here and write him as HCO3 minus plus H2O. And Matthew, what do I write on the other side? He's still got more hydrogen to give away, and that's what we're trying to show.
So H3O plus.
That. He still has hydrogen to give away.
Yeah. So H3O plus.
And, okay. I'm sorry. You said it, and I was doing the CO3. Okay. H3O plus, and then you're left with CO3 minus 2. Agree? Because he has 2 hydrogens to give away, he has 2 dissociation equations. Because he has 2 hydrogens to give away, he has 2 dissociation equations. If he has 3 hydrogens to give away, he has 3 dissociation equations. Now, here's the good part. It's only the first one that really matters. It's only the first one that decides the pH of the solution. But we do have to know that there's more than one dissociation equation.
We'll make you run the battery with that.
Yeah. All right, so quick question. Who remembers Hess's law? What's Hess's law mean, Brianna? Combining. Can you take those 2 dissociations and combine them into one? You can. It's called Hess's law. Well, let's do it. Let's take those 2 dissociation equations right here, and let's combine them. Who cancels out? What do you call HCO3 minus since he canceled out and he was a product first and a reactant second? Well, yes, he ends up. Okay, we're going to get to an intermediate. Yes, you're not wrong, Matt. We just haven't gone there yet. All right. So you're going to put them together and you're going to get H2CO3 plus 2H2O yields CO3 minus 2 and 2 hydroniums. Yes? Now, that's not the equation we end up writing down because it really does happen in 2 different steps. Step 1, he's got a Ka1. Step 2, he's got a Ka2. Put them together, the overall Ka. How do you get the overall Ka if you have a Ka1 here and a Ka2 here and you just added those 2 equations together? Thank you. Oh, thank you. Multiply them. So his Ka1 times his Ka2 to get the overall Ka would have to be multiplied. Isn't that called the multiplication rule from the last unit? Didn't you see that on your test? I did. In multiple choice question, I did. Okay, so the difference between strong and weak is double arrow versus single arrow. All right, let's stop a second so that doesn't get too far and too long because then I'll get in trouble because it'll be past 15.